forgot I tried to catch my chalk and then lost it at the end of the last video. What we're going to do now is we're going to look at what's called the first and second derivative. Now the first is just the derivative that we've already seen. The second is essentially you do some differentiation again. We're going to look at what they actually mean and what you can use them for. I think my titles are getting longer and longer. So there's something that we've done, I've hurt my back. There's something that we've done called finding the derivative. We're happy with that. If we have a y, we find dy by dx. So let's have a little example. We could find dy by dx. But what we could do is we could differentiate this and find what's called the second derivative. First derivative, what we're going to do is called the second one. So the way that we write it, we don't do that. Although it's right, we don't do that. So what we do is that a little 2 there and a 2 there. This means the second derivative. So we're going to do that one again. There we go. That's it. That's first derivative, second derivative. Nice, but what's the point of that? Well, if that's your curve, this is the gradient, this is the gradient of the gradient. This is showing how the gradient changes. And there's a few interesting things that we can do with that. So let's tidy this up and look at what we can do. Okay, this is just a summary of what I just said. So we've got our y is our function, but we could also have it as f of x. And then dy by dx is our first derivative. But what we could also have is very small f prime of x. And then the second derivative, this one's got little 2's, we could have f prime prime of x. If we were to keep going and on, we'd just add numbers there, like that. That's n. And then for f of x, we would, instead of putting loads of dashes, we'd just put a little n, a tiny n, and that's the nth. That's not ninth, it's nth. Right, what I've just realized is in this video, I'm not going to look at using the second derivative very much. So I'm just going to delete that, and it might be a bit of a shorter video. So we've got all this different notation. What I want to look at is what the first derivative means. So let's have a random little function. Okay, first derivative, let's plop that in. Let's do that. Right, what does it mean? Well, we could put in some coordinates and find what it is, right? So if we put in, say, x equals 1, we'd get dy by dx is 12. That means that at the point where x equals 1, the gradient is 12. Exactly there, it's 12. But there's two little concepts which we are interested to find out about. And one is a function increasing or is it decreasing? So if I draw this, the 6x squared minus 4, right, that's that. What we find when we look at this is that here, the gradient's going down. If something's going down, we say it's decreasing. If we get to here, it's flat, then everywhere after that, it's increasing. And if we put in values of x into here, we'd see that if it's positive, then obviously it's going up. So we call that increasing. If this value of the gradient dy by dx was negative, then it would be decreasing. So it gives us this little interesting point of an increasing and decreasing function, these definitions. Now let me write these for you. So what we have, right, if our first derivative is greater than 0 at some value of x, then it's an increasing function. The original function is increasing at that value of x. If it's less than 0, then it's decreasing at that value of x. So for this example here, now it probably seems a bit obvious, but this is what we use it for. Now, have a look. This is kind of it. So let's have a look at a more complicated example. Okay, here's our little example question. We've got our function 3 over root x, and we've got this point x equals 9. What we want to know is, at the point x equals 9, is our function increasing or decreasing? So what we need to do is differentiate that. Well, first we need to simplify it. 3x to the minus half. Now let's differentiate it. Gone a bit small. Minus 3 over 2x to the minus 3 over 2. We're going to put 9 into that. use my lovely little vertical line in an x equals 9. Means we're putting 9 into dy by dx. I'm going to do this in my head, it might take a moment. Minus 1 over 18. I'm going to check that. Times it by minus 1. Bam. So since dy by dx at x equals 9 equals minus 18, which is negative, so at run out of space. X equals 9, y is decreasing since now this is just a practice for your communication technique. If you just finish there, right there, then you have not finished the question. Writing minus 1 over 18 is, it's the right answer, but if you don't finish by actually saying what it means, then someone's going to have to interpret your answer, and although like an examiner or someone like myself knows what it means, they want to know that you know what it means. It's a bit like what Alan Sugar once said in The Apprentice. He said, like, if you get hit by a bus, then if everything was in your head, then how can someone else pick up your work? If you wrote down that, how does someone else know what your conclusion was if it was in your head? Buses. Just remember buses. Right. So if it's greater than 0, it's increasing. If it's less than 0, it's decreasing. What about the one thing that I've not mentioned? What if it's equal to 0? Right, what does it mean when the gradient is equal to 0? Well, it means that we haven't got a little diagram. Decreasing, 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 flat. Increasing, 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 increasing. At this point here, that's where the gradient is 0. We've got a special word for this. It's called a stationary point. So I'm going to add that onto there, and that'll look great. So we've got these 3 different situations. Now, I've not spoken about using the second derivative yet, but what the second derivative can do is tell you the nature of that stationary point. The graph that I just drew, it was down there. But what if we had something like a quadratic with a negative x squared coefficient? It's like that. So the gradient of the gradient, i.e. the second derivative, tells you whether the gradient is going from to a more negative, right? The gradient's going more negative, and here the gradient's going more positive. So if the second derivative is positive, then it's a minimum, one of them. And I'm going to talk about those in a later video. I want to do one last question, a nice old spice. Okay, this is the question I want to focus on. Now I've kind of really shafted myself in terms of space on this chalkboard because I'm keeping this. It's right in the middle. So we're going to squeeze this on. We want to show that this function for k being greater than 0 is increasing. So we need to show that it's always increasing for k greater than 0. So the first things first, what are we actually trying to do? Right, it's increasing when that's positive. So what values of x will make that positive? Interesting. Well, we know we need to differentiate, so let's do that. All right, we don't know what k is, but it's a constant. So a constant times x differentiated is just k. And we want that to be greater than 0. Not just k greater than 0, this greater than 0. So what we need to think about is, what does this look like? Well, the derivative of that is a quadratic. We want the quadratic to be greater than 0. So what we need to think about is, when is it equal to 0? Because that's when it crosses over from being greater than 0 to being less than 0. So let's say e equals 0. Now what we need to do is solve. So let's do 3x squared equals minus k divide by 3, and then square root. Hold on. See what happens there? That if we originally said that k is greater than 0, then this can only be positive. So minus k over 3 is only positive, and hence we're doing the square root of a negative number. So, oh, right, so the original question said that k has to be greater than 0, which means that this bit inside the square root must be negative then, because it's a negative of a positive number. But the square root of a negative does not exist. So I said that this is not real, because really that's what we're talking about, since k is greater than 0. So your final bit of ending this would be hence dy by dx is greater than 0. But what about, has this actually answered it? Because I guess it should be that. So what about if it was less than 0? Well, do we need to worry about that as much? The thing is, right, what we're trying to say is that if we've got this quadratic, and that k, there's the quadratic. The k, what it does is it moves it up and down there. But if k is only positive, then what it's doing is only moving it up. So what we're saying is that it never passes the x-axis, because if we put it equal to 0, it's never gonna, there's no solution for that. So it's never ever gonna pass the x-axis. So, job's a good one, it's done. Now I've got one more question, squeezed it on. Find the value of x such that this big function is decreasing. So we need to find the derivative when it's less than 0 of this. So first things first, let's differentiate. Right, so we've got a nice little cubic. We want to do this less than 0. Now it's nice again, like we did here, we drew a little sketchy root. We're going to do the same again. So we've got dy by dx is all of this, but it's a cubic, so it's going to do this. And it's going to cross the x-axis at some point, like that. So what we want to find is all of these values of x that make it under the x-axis, and all of these ones here as well. Really, I've shaded the wrong bit. So we need to find this value of x, this value of x, and that value of x. Now I know it's like this because it's a positive coefficient on the x cubed, so it does that. So the values, we need x is less than something, and then x is in between something, which is going to make this less than 0. How do we do that? We've got to solve a quadratic. Sorry, this is a cubic. We have to solve a cubic. Now, solving a cubic is quite tricky. What we first have to do is find one thing that works. So I'm not going to try 0 because it'll just be minus 3. So let's try 1. 1 add 3 is 4, minus 1, minus 3. Okay, so 1 works. So 1 is a factor of that. So what you could do is then say, since it's x plus 1 works, right, this is factor theorem. If x plus 1 worked, then this cubic can be expressed as x minus 1 times some quadratic. Now our job is to find that quadratic, which we would do by polynomial division. Or, I'm just going to put it in my calculator and solve it. So the good thing about these calculators, equation solver, the degree of this polynomial, it's a cubic, it's a degree 3. So you type it in, press equals, and we've got one answer is minus 3. So this is what the calculator said. It's solved this for when it's equal to 0, which means it's found those 3 points. Minus 3, 1, and minus 1, which means that point must be minus 3. So to answer the question, decreasing, so when x is less than minus 3 and x is between those two values. That satisfies me. That is good. So what we just did was we differentiated. We wanted it when it was less than 0, so we considered what the graph of that gradient function would look like and where it would be less than 0. So we solved it for 0, used those answers to set up these inequalities. And I solved it so easily using my calculator because you can do that. If you didn't have a calculator, you would use factor theorem. Nice. Right, I'm going to stop there. Next time, I'm going to look at actually using differentiation to find tangents and normals and maxima and minima, and using the second derivative. I've introduced it now, but I've not really spoken about it much. Interesting, that, isn't it? Yeah. Save it for next time because I've gone on too long.